Here we're going to talk about a different version of NIM. It's called two-dimensional NIM. This is introduced in, I believe, exercise number 6 in section 3 here, or chapter 3 here. Two-dimensional NIM is played on this quarter infinite board. That means it's infinite out in this direction and it's infinite in this direction, with a finite number of counters or squares. Here we just see an example position with 4 squares, but you could have any finite number of squares as an initial position. I'm sorry, any number of counters, these little circles, as an initial position. A move consists of taking one of these counters and moving it anywhere to the left. So this one can't go to the left, but this one, let's say we're starting with this counter, it could be moved 1 square to the left. Or instead of that, if we choose, we can move it anywhere on a row below. We could move it to here, we could move it to here, or we could move it 1,000 squares to the right and down 1 row. We can move it anywhere on a row below. We could move it down to the first row. It can move on to the same square where there's already a counter. So there could end up being 2 counters here, or any number of counters on a particular square. That's fine. So those are the allowable moves. Here's the first question. Is this a progressively bounded game or a progressively finite game? Remember, we have 2 players that alternate. Each player in turn will make a move, an allowable move, as we've just described. When all of the counters are down here in the lower left square, no more moves are possible and the game is over. Well, I'll tell you right away, we can see it's not going to be a progressively bounded game. Why is that? Let me erase all this stuff that I've written here. For a particular starting position, say the starting position shown, it's easy to see that there's no way you can bound the number of moves that will be necessary. We might take this first counter and move it 1,000 squares to the right on any of these lower rows. It might go 1,000,000 squares to the right. And then one just might move it left 1 square at a time. So it might take 1,000,000 moves. It might take 100 million moves if this counter is moved even further to the right. There's no limit. However, it is a progressively finite game. The game will end eventually, no matter what. In each move, we move either, look at the highest counter, it either moves to the left, closer to the end there, or it moves to a lower row. Eventually, the counter in the highest row will move all the way to the left and will be forced to move to a lower row. It might be way off to the right, but it will be in a lower row. And then you can go down and look at the next lowest row that has a counter. Eventually, those will be moved to the left or to some lower row. And we keep going and going until eventually every counter gets down to the lower left square and no more moves are possible. The game will end in a finite number of moves, but there's no bound on how many moves that will take. Can we talk about the Sprague-Grundy function for two-dimensional NIM when it's not progressively bounded? The answer is yes, but we're going to have to use ordinal numbers. When a game is progressively bounded, just the basic procedure we've outlined before and talked about in class will get you, will allow you to create the Sprague-Grundy function for any position, and there will be some finite number. But now, as I said, we're going to need to use ordinal numbers, and I'll show you why. Let's say we want to know the Sprague-Grundy function for an initial position in the game of two-dimensional NIM with just a single counter. Well, if we have a single counter here, and we want to know what's the Sprague-Grundy function for this position, well, let's just start here. The terminal position, I'm going to erase that now. The terminal, we imagine we have 1 counter. The terminal position gets a Sprague-Grundy number of 0 because it's terminal. This position here to the right gets a Sprague-Grundy number of 1 because its only follower, the only place things can move, would be to the terminal position. Imagine a counter here. The only place you can move from this position is either to one of these two squares which have a 0 or 1, so it gets a 2. So I'm drawing in the Sprague-Grundy values, the values of the Sprague-Grundy function for these different positions, and it's easy to see that they just look like 0, 1, 2, 3, 4, 5, 6, 7, etc. along the first row. But what if we have a counter here in this position? Well, it can't move to the left anymore, but it can move to every one of these positions in the lower row. So what's the minimum excluded number? Well, it can't be 0, 1, 2, 3, 4, 5, 6, 7, or any natural number. So here's where we have to start using infinite ordinals. And without going too deep into the set theory, we can talk about ordinals in the following way. We start with just ordinals for the natural numbers. 1, 2, 3, 4, 5, etc. The ordinals are a well-ordered set, and we give a name, omega, to the smallest ordinal that's bigger than any natural number. And then we have the next ordinal after omega is omega plus 1, omega plus 2, and then they keep going. And the next ordinal that's bigger than any of these would be 2 omega. Then we'd have 2 omega plus 1, etc. And then we'd have 3 omega plus 1, etc. And we keep going down like this. We'd have 4 omega, it's 4 omega plus 1, 4 omega plus 2, etc. And if we ask what number is bigger than all the natural numbers, any number of this form, this form, this form, etc., bigger than all of those, we would get omega squared. And then, of course, you would have omega squared plus 1, omega squared plus 2. I didn't write that correctly. We'd have omega squared, then we'd have the next ordinals, omega squared plus 1, omega squared plus 2, etc. Ordinals can be divided up into two types. An ordinal like 3 is a successor, or the next number after, or the next ordinal after the number 2. 4 is the successor of 3, 5 is the successor of 4, etc. Omega is what we call a limit ordinal. It's not the successor of any particular ordinal. It's a limit ordinal for this sequence of the earlier ordinals. But then it has a successor, omega plus 1, omega plus 2, etc. 2 omega is a limit ordinal for these. 3 omega is a limit ordinal for those, etc. Omega squared is a limit ordinal for all of these above it, all of the ordinals that are smaller than omega squared. So what does that tell us about the Sprague-Grundy numbers if we're allowed to use ordinals? Well, the Sprague-Grundy number for this position here, just above the 0, would be the least thing which is bigger than all the natural numbers, so that would be omega. Then we'd have omega plus 1. It has to be the least thing that's bigger than omega and everything below it, because all of those are already taken. We'd have omega plus 2, etc. Above here, we would need the least ordinal that's bigger than all of these things here, which are the numbers in the ordinals in the second row. So we'd have 2 omega plus 1, etc. We'd have 3 omega plus 1, 3 omega plus 2, etc. And it would continue like that, and we'd get the Sprague-Grundy function for every position in this playing board for two-dimensional NIM. Now, how will that help us? Well, after we get the Sprague-Grundy theorem and talk about sums of games, we'll be able to kind of extend it and generalize it to a form that allows us to deal with progressively finite games like this, and we'll be able to make sense of the position that you see, this initial position. Let me get rid of all the junk here. This initial position, which consists of 4 counters on the board.